Test. Okay, okay, that's good. All right. Now what? All lights on. Okay, cool. Um, okay, all right. It took me a couple of minutes to set up today. That was something weird going on with the mic. It didn't want to. Uh, is this working? I can't tell. Anyway, I ended up having to restart the thing and try to get it to connect again. I think it's working now. So let's get into it. Last class, we talked about Lucas Canadi. That is also your homework. There's a lot of um, files and other sort of utility stuff in the homework, but don't let that intimidate you. There's really only one thing that you have to be actively working on, and that's the Lucas Canadi implementation. And I feel like I've put in sufficient detail in both the like markdown readme for like how to set up and everything, and also just the problem statement so that you understand what the expectation is. But a like high level overview is you do the whole thing just the really bare bones basic version in NumPy, and then sort of iterate on that by doing it with the pyramid approach, and also do it iteratively. And then you'll see why those two things are useful. And you have been provided the OpenCV implementation because that it uses corner detection initially and then passes that to do optical flow. So we sort of called that garbage initially while talking about using features for flow estimation. It does make sense why they do it, but as far as calculating flow itself goes, we want to know how that's done sort of naively, how you would develop an approach that does that. So that's what we're doing. And maybe after class, I could like try to just demo some of the stuff to give you a sense of what is expected, or like if things are taking a long time to run, whether that's normal or not. That's a question that came up. So I just feel like giving some context of what the expected output looks like, or what the other things are, how to interact with it. I'll probably go over that at the end. Uh, I just want to be careful not to show you guys the actual solution because it's like in the same folder. So time permitting, which I believe it should, there's not really a lot to farm back. Yeah, so let's get into that. Is there, homework 3. Anyone have any trouble with that, or was everyone able to turn something in? I didn't get a chance to look at it yet. I think Hima did. I'm not sure. I'll be talking to her tomorrow probably.
First one was easy. Enlargement filter was a little tricky to implement. It took some time to actually see the pixels being disordered.
Okay.
But yeah, I was able to manage somehow and apply some filter.
Did you think it was fun though? Yeah. Second part, I mean, so how I ended up asking you guys to do that was my goal was to come up with something that once it ends up in the like submission repo, when I look at your outputs there should be a fair bit of like variation. So with the overlay part, that's easy because I'm only giving you guys one, and then the other two, whatever you pick, that should result in something different. But for beyond that, so that came from like Snapchat filters. That's what I was thinking about trying to have you guys do. Before that, I was thinking of having you guys do like a music visualizer that analyzes I don't know, your like facial expression and sort of reacts to that in a feedback loop. That along with also analyzing the like the tone or energy of the audio and also the lyrics and sort of fusing all of that. But then that felt like way too much. So this is what I ended up going with. Um, and I'm not sure if that's actually how Snapchat or whatever else wherever else you would actually find that in practice, whether that shifting of pixels outward, inward is the way they do it, but looks close enough, I guess. So, um, yeah.
Not about the custom mask to add one more
Uh-huh.
right like headphone mask which covers the whole face. But like it was covering only till here, it was reducing the
What did you add?
headphone mask.
Oh, okay.
So is it because like on the code, the like template code you gave, we were considering only eyes, right?
Yeah.
Is it because of that? Like I thought it might be because of that because we are not adding any other like ears and all, we are not considering to.
That's a good point. I mean, I only were you marking other landmarks also? Okay.
Eyes and more antennas,
Okay. Yeah, that I think maybe if you mark like the mouth and stuff also, and like when you're doing the key point marking after you segment it, if you mark the mouth, I think that it should work. Because I tested it with just eyes, the eyes and nose, and that's it. I didn't use a different mask apart from the one I gave you, so I don't.
cover one skill that those or something, those not so fine, but
Okay.
both based on like content relatively.
Hmm. Cool. Okay. Glad to hear you guys engaged with it, I guess. Even if you didn't necessarily enjoy the entire process. Um, the fourth one, what is it? Oh yeah, optical flow. Yeah. Uh, that also has some cool stuff that you can do with it. So I hope the experience is similarly gratifying once you figure it out. I don't even know if I'm going to get to see this, but this is for course evaluation. So if you guys want to take a few minutes to do that, either now or after class, either is fine. And this is in the slide, so you could also do it later. But I have heard of professors sort of incentivizing this by saying they'll give some extra points. I'm not sure what the ceiling on how much extra I can do is, but I will check with my mentor and see what to do about that. Um, I don't know, maybe if like there's only what 28 of us, what's 80% of that? Just ballpark. Okay, yeah. Yeah, if I hit 80%, not like score, but number of people who did this, then I don't know, some extra points. I'll figure out what that is, um, how much I can do, and I'll do something if we hit 80. Um, There was one other thing. Oh, also the cheat sheet that you can bring for the exam. That's also something I'm going to confirm, but tentatively 4 sides is what you will get. So today we're going to build on optical flow. We looked at Lucas Canati earlier, and one of the closing points that we made about that was that it was sparse, and we wanted something that was dense. And um, Hornbeck and Gunnar, I believe, are the names of the people. We have this thing still on. Okay, yeah, it is. Two-frame motion estimation. This was in 2003 as opposed to Lucas Canati, which was, I think, like 20 years before that. The initial assumption here is the same. We assume that the object moves by delta p over delta t time steps. And by time steps, we just mean how many frames. If it's the same frame, it'll just be a t, and if it's two or frames that are separated by more than two, then we'll just shorthand that with delta t. So we used the first order approximation earlier. Hope you guys watched the 3 blue, 1 brown Taylor series approximation video, because really helpful to sort of put all of this stuff in context. But basically, we were trying to fit a line to the trend of distances that we were observing, or like based on change in intensity. So what's better than a line? You, you could try to fit a curve instead of a line, right? So that's a bit more complex, and odds are you'll fit it to the distribution of points a bit better. So a line we were able to represent with just two coefficients, which is one of which was the slope, and then we have a bias term of sorts. Instead of that, we're going to try to fit a curve to this. So now there's three coefficients that we care about to represent it. And to find those, we will be using the Taylor expansion again. And since we're dealing with pixel values and matrices, it's just useful to have stuff to treat stuff as vectors. So to square the x over there, that's how we would square it. The order of operations being important. So to remap the terms from our initial assumption and put that into a second order Taylor expansion, it unpacks to this elaborate mess. But there's, again, really not a lot going on. There's A, B, C terms that we care about. So A would be a symmetric matrix, B would be a vector, and C would be a scalar. And these are, this is the first image and parameters from the second image. So the sort of indexing over which image we're looking at is represented by either having just a t as we do over there, or t plus delta t. And similarly for our flow vectors. So there's this correspondence between both the sides of the equation, from which we can reduce that by canceling out those terms, which leaves us with just AT equals the A matrix for the next frame. We do the same thing for the B terms and get a correspondence over there, which gives us this relation once we get rid of whatever is common. This doesn't tell us anything directly, so this is something that we'll have to solve for. And we do the same thing for the C terms. So this is just that one coefficient without any other stuff to worry about on that side. And we say that that equates to this whole expression where we do care about the flow vectors being squared, the A, B, and C terms. There's all of those. So we'll have to work our way up to figuring out this part. So the first thing to solve was the equation for the B term. And we want to find flow. So we solve for delta P, move stuff around a little bit, which rearranges to that. And least squares over a small neighborhood. What we're doing basically is kind of like finding a good set of values within the ABC coefficient matrices and vectors that would minimize the difference between the first and second image, kind of like how we minimize mean squared error when we're doing deep learning, but it's just we're not normalizing by how many terms we have. So we consider a small neighborhood. This is 5 by 5 over here, and we solve it pointwise. So unpacking that, we can represent it using a bunch of matrices. So we have our X and Y that we're trying to find for flow, since we need it along both of those directions. And that equates to intensity value at that position. But we're trying to decompose it so that we can get the relationship between intensity and individual coordinate values. And then to find the ABC terms, we would find a set of values that would minimize the squared error, but we don't know whether this can be solved closed form, whether it can be inverted directly. So I jumped the gun a little bit with the least squares minimization, but so one of the things that we got earlier over here was that AT equals T plus delta T, and that's what does that imply? That would only be true if the contents of the initial frame and the subsequent frame were the same. But for our problem statement, that's not true, right? Because we're trying to find movement, which means the content in both of those frames has to have changed or there wouldn't be any flow. So we update our assumption a little bit and sort of plug in that domain knowledge that we have about the problem that we're trying to solve. So instead of just considering the two of them equal, we know that there's some motion, so we average the two of them together and just call that A. So there's only one A term that we need to worry about. That simplifies our problem a little bit. And on the other side, whatever we have, we just call that delta B, because this is, again, averaging the difference between the two of them. And once the whole thing is held nicely packed like that and simplified, we make the same assumption we did with our initial naive Lucas Canary. And do it for a bunch of pixel locations rather than just an individual location. And then we can apply least squares again. And you'll notice that there's something in addition to all of the ABC and flow terms that we were talking about. We're adding a Gaussian weight, and that's to emphasize the center flow in the center of the neighborhood, since each neighborhood, when we're trying to estimate flow, we want that response to stand out, so that once we put the whole thing together, regions that are around that are away from the center won't contribute to it as much, and we're able to sort of apply that to the entire image in a way that once you put everything together, it will be uniform in its importance. So that image that we had initially, or just any example that we've seen of where you would use flow. So if there's a tree up close and there's a house in the back and you're driving past it, you'll see the tree move a lot more than the house in the back. And if your neighborhood is on a region that includes both the tree trunk and the house in the back, then you're going to see more flow for the tree. So this assumption that delta P is constant for the entire neighborhood doesn't hold. But one way we can reframe what we're looking for is by saying that, well, whatever change you see for that particular neighborhood, rather than thinking of it as motion, we can think of it as an affine transform that gets applied to that neighborhood. And we just want to try to find the parameters for that transform, which is rephrasing the problem a little bit, but we're essentially still trying to find the same thing, just what transformation leads to that change that we would find. So we represent that using this set of variables and their coefficients, and there's A1, A2, A3, 4, 5, 6 over here, and then 7, 8. So this should remind you a little bit of our translation operations, rotation stuff that we did early on. And we're estimating both of those simultaneously. So plugging that in here. So this is replacing our flow estimation with figuring out what the affine transform is, and that makes it a bit simpler to know what exactly we're looking for. And then we can apply least squares, unpack the whole thing, and try to find a set of values for the coefficients in here that would minimize the difference between all of them. And there's an inversion again, but since we have a whole bunch of equations by virtue of having a larger neighborhood, we're also doing weighting. So in practice, what tends to happen is that this is a lot easier to compute than trying to invert the initial form of this expression. And this is applicable to the entire image and is not bound by there being a good feature response when we try, because we're not dependent on gradients anymore when we do it this way. And that is because we're doing the second order version instead of first order. So going back, for first order, we were trying to find slope and the intercept, y-intercept for the line. Yeah, so that M over there is by Lucas Canati. We needed to mess around with gradients. Here it's less of a concern. And yeah, far and back. So I'm not. This is not something that is part of the homework. Don't expect you to implement it, but just understand the intuition for why this works and um, how we got here, basically. So yeah, far and back. That's the algorithm. Maybe once the semester is done, if you still have a lingering question about it, you could try to build it. But since we're still good on time, what I'm gonna do is I'll pull up the homework and go over what is expected. Um, and I'm gonna have to be real careful with that because I don't want you guys seeing the code just yet. Oh, I also have to upload homework 3, my solution for that, which I will do tomorrow. Okay, so, oh, no, 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 no. There we go. Okay, that was the version I gave you guys anyway, so no harm done. That even if you went back to the recording, you wouldn't catch anything. Um, Let me find where my solution is. Oh God, do I not have? Where did I put it? Okay. Oh right, yeah, I made a different branch, of course. Check out solution. Let's have all of it. Oh, this doesn't have any of the outputs. I gotta rerun the whole thing. For that, I guess what I can do is select, collapse all code. Yeah, okay. That's cool. No. Oh, it already did it. Should have been paying more attention. Restart. Um, okay, I think we should be good now. Come on. Okay, did I move between those? I can't really tell, but I guess the rest of it will tell us. So the first one up there was just visualizing flow using OpenCV. So you don't have to implement anything for that, but this is the kind of output that we want to mimic with what we're doing in the homework. It's not going to be as good as this implementation, but it's similar enough that the principle of it should become clear. So um, okay, so I have a definition for Lucas Canadi in there, which I will not be showing you. But the kind of output is, I get weird outputs sometimes, and it takes a while to run. I think like 15, 20 seconds. Um, I can't tell if this is still running. Is it? Okay, yeah, it's doing its thing. So yeah, there's something in there, but it's not great. There's some flow information, but ideally we want it to be more like the OpenCV one. So this represents a lot better which direction I moved. So we're going to improve on that. There's a few problems with this. One is that it's really slow, and the other is that our flow isn't really representative of what actually changed between the two of them. And one of the hints that just what's going on in here should give us is that maybe it's a multi-scale thing. So if we sort of zoomed out and looked at how everything moved and sort of zoomed into a patch and see how much it moved, then we might be able to get information on flow that we can then combine. So that's why we do the pyramidal approach, where we downsample it a bunch of times and then calculate flow at all of those scales. Uh, that, okay, warp. And then we got to combine all of that. Visualize pyramidal, okay. And the intended workflow that I had in mind was, so once you're able to get to like this point, um, then you would take that implementation and plug it into the .py file where there's another Lucas Gennady function, and replace it in there if you want to mess around with the CLI that lets you do a couple of things, and then sort of iterate on your actual algorithm until you get to the last step, and then plug that in here. So this seems to be a bit better, but we have some like stray flow vectors that aren't necessarily what we want to be seeing in there. For the most part, I'd say that these are close to what they should be, and that this one that's going the other way has to do with the background and me sort of getting the foreground out of the way, which you can think of as the background moving the opposite way. And that's where it's starting from. So that's how that ends up in there. And then it's still slow. It took longer than the naive one, because obviously we have more computations for calculating flow at multiple scales in it, as opposed to just doing it for the single one. So to deal with that, we sort of break the problem down and do it iteratively instead of all at once. And what we're doing is using the flow estimate to sort of create a, we have an initial image, we have a second image where something moved, we estimate flow, and then see how what the original would have been like um, based on that flow estimate, and see how far off that was, and do that a bunch of times until we get our final flow field. Oh, hide that. Okay. Iterative. That runs a lot faster. Um, and we still have some flow information, but it's missing flow values from different scales. So the idea is to combine all of that together. And we have this mess of flow information. So this could be corrected with some tweaks to the combined, the visualization function, where you could have maybe like normalize it somehow, but we don't necessarily have to worry about that because oh, direction looks kind of off. I might have to work on my solution a little bit, but in principle, it's doing what it should, and we do get a sense of what moves where. Uh, and then once you have your implementation done, then what you would do is, how do I run that? Open up terminal and just need a second. Um, okay. Pull this up here. And I want to move in there. It's not like spaces. Oh, is that not it? What up? Oh, right. Okay, I'm just going to do it with the inefficient way to do it. Oh, that's how it, oh, it's the angular brackets at the end. G, okay. Homework 4 and okay, so I do have everything in here. Want the what did I call it? CSE 573 homework 4 and run the main script, and this same mode, and I'll run the OpenCV one first. At least I think that's what the, forgot what the parameters were. I don't think there's anything for you guys to do in here, so I can, okay, OpenCV flow, that flow, this mouse control, right? Okay, that popped up over here. So that's it. This you have been given. Oh, I gotta give me a second. Like, oh, yeah, I think that should be better now. Okay, let's try that. I'll quit out of this and run it again, maybe. Just Yeah, so this, unlike the other flow fields that we saw, it's only showing it for points, which is sort of what I was talking about, why we don't want to get into the details of how the OpenCV implementation works, but there is a feature extraction step initially, and then those are what's being tracked, and it's a lot more robust and efficient than what we're doing for the homework. So maybe dig into the OpenCV source and see how that differs if you're curious. So apart from that, we also have a deep learning equivalent of that, which represents it a bit differently. Yeah. And this, you might have a hard time running this if you don't have a GPU that you can push stuff on. And that, okay, so I'm gonna, hmm, um, yeah, if I stay still, it should sort of go quiet. And then when I move, you'll see more pink there or magenta or whatever. But this is it's a lot more dense compared to even getting it for a whole grid of points, because you know sort of how much each pixel has moved, since it's of the same shape as the image it's being overlaid on. Uh, and then, um, okay, yeah, whatever. I'll run it anyway. My solution is not great, and building a great solution isn't really the point, but just being able to do it. This I don't remember if I integrated all three of them together for plugging it in here. Yeah, this is not bad. Uh, so before you do the iterative part, it's gonna run really slow, but this has that also. So the faster I move, the stronger the arrows showing up. When I move pretty slow, it doesn't really get that worked up about what's on there. So you should be able to plug in your implementation of Lucas Canati in the .py file and see something similar, even if not necessarily the same. So yeah, you now have a sense of, and this isn't like running on CUDA. The CUDA, yes, is just that I have a GPU, that's all. Yeah. Why are we doing all of these things? There is hand pose, which I'm using MediaPipe for that. Uh, I was initially considering having you guys also like load up a pre-trained hand pose estimation network and interacting with it, but felt like a bit much for a week. Um, so, uh, so I'm not doing it the way that I would have asked you guys to do it, which is by loading up a model and understanding its encoding and using that, but instead we're just using this. So I will be using the location of the thumb tip and index or pointer and the middle finger downstream. So we can do a bunch of gesture stuff with this. The tracking's not bad. Considering we don't have depth information, it's still able to figure out pretty quickly where each joint is and which finger it is and so on. Um, quitting out of these, if you simply closed it, it'll just pop back up. So you want to press Q on your keyboard, and that exits out of the script. And then we go to mouse. Is it underscore? Yeah, it's all underscores. Mouse control. And so now I didn't pass any of the use flow options. So what it's going to do is it will just take the absolute position of, so this is a baseline, basically. We don't, oh yeah, my hand's in here. And I don't know how this will work with the multiple monitor setup, but the mouse should also move. I can't remember where to go. Oh, okay. So it defaults to the center of the primary display, I believe. So I'm gonna switch out and put everything up here. So I think it should work now. And yeah, there we go. And if I come down here and if I join my middle and thumb together, it should let me right click. And I can, oh, it's kind of hard with these lighting conditions, but it's a proof of concept that this is something that can be done. I don't think you can click and drag things, but only do individual clicks. Yeah. Undo, yeah, all right. So that's how it would normally work. And you can choose to use flow, and I'm going to use raft. So now instead of using the absolute positions of my, oh, what happened? Oh, it started already. That's my bad. Instead of using the absolute position in the first frame and the second frame of my thumb, and just having the GUI library figure out how to move it, we are supplying, we're estimating what the new coordinates should be based on flow, and we're not directly supplying the location of the thumb to the next frame. And seems to be a bit smoother, wouldn't you say? It's not as jittery as the other one. It's a bit more stable. And I'm gonna try to minimize that. Yeah, there we go. I was pretty happy with how this turned out. Had a lot of fun building this. I also wanted to pull my hair out, but it worked in the end. So now you guys are gonna have to do this too. Raft, and then yeah, you'll be able to use the whatever you build. Yeah, I can call it mine. That's the argument. And okay, thumb is up there, and it's not as robust as using Raft, but it's still something that loosely correlates with what we're where we're trying to move. I think with better lighting conditions, you guys will have an easier time doing this, but yeah, have fun with it. What happened here? Oh, it went too far. Um, that's all right. We live and we learn. Uh, okay, so I hope that it gives you some something to look forward to building, and also just a sense of what the end result should look like. Um, Anyone have any questions? Yeah. Uh-huh. Yeah, I mean, when we're just writing down what problem we're trying to solve, we would say the AX equals B part. But when we want to do it as matrices, then the way we square things and just how we represent that changes. Hmm. Oh, to like, okay. Hang on. I gotta go back and check what I did. Visualize one. Oh, this has everything in it now. Where's my playground? This is not, okay, it's not up. It's cool. Flow, we got flow. Okay, so grayscaling, initialize the flow field. Think I, okay, spatial gradients, temporal gradient. And then we got nested for loops going over all pixels in X and Y. And then we get a bunch of responses for each window, depending on what neighborhood we're looking at, and then stack all of that together. And then, yeah, determinant linear algebra. And yeah, inverting it with NumPy, the linalg dot invert is what we're. It's the NumPy equivalent of all of the other stuff before it. So fair game. Oh, hmm, I didn't. Okay, let's see. Least squares NumPy. That's not how I have it in my solution. Mine is kind of like MATLAB syntax. Uh, least squares NumPy. I gotta check. But yeah, even if you do least squares built-in function. Okay, what does this expect? A B. Um, A X must be computes the vector that solves it. A transformation. Hmm. Coefficient matrix. And we have a second one, R condition cutoff ratio for singular values for the rank determination. I haven't used this, so I can't say off the top of my head how much this would reduce, but I think it's just like one line that changes really. Um, um, Flow YX invert. You can do it either way. It doesn't matter to me. All I care about is that it looks right and you're not just directly calculating it on OpenCV. That's pretty much. Mm. This is Copilot. So I didn't read through the comments in here. The other document. I'll check and get back to you. If there's changes to be made, I will try to make them. But yeah, if anything up there in the comments or whatever feels off, just um, stick to what's on the slides, basically. This is just for like quick reference, whatever I could throw in there last minute. Um, yeah. Okay, cool. That's it. But we're done with flow. And for tomorrow, I'm thinking I'll do review. Is there any, I mean, I'm gonna go over all the quizzes that we've done so far and see what parts seem to be problematic and maybe start with those. But if there's any that you guys want, maybe like post on Piazza or something, and I'll dedicate some time to that part. Uh, yep, that's it. You're free to leave. I will see you all Thursday.
For the assignment 4, we need to submit the RTND file, right? It's like there's no code changes for this mouse movement and graph.
Hmm.
We have to experiment.
Yeah,
Just have to experiment.
the Lucas. Wait, hang on.
Doesn't matter. The app is
Raft is fine. There's no graded component for that.
working. Everything is also working, but we need to create a video.
There's no. Give me a second. Uh, okay. Let me go back to check out.
So I feel like once you're used to it, it's probably. I've never used it. I would say, like, even if I could be
Okay. Um, oh God. No. Oh, okay. I thought for a second I gave you guys all the solution already. Okay, so if you look at, wait, let me just close everything. So up here, if you go to this here, yeah, either so if you do the first version, just the normal one, it's going to be really slow, so you barely see anything happen.
Device is like creating a still picture, but I'm not able to move. And it is stuck there. I'm not sure is it because of the GPU limitation or something, but these things are working. I mean, basic.
The OpenCV one, are you saying OpenCV flow when you try to run that, that doesn't work?
First one,
Mm.
So what you showed in the demo, right? It's showing a great mesh like this.
Mhm.
So that thing is not working. My video is getting stuck with the first frame.
Google Lens.
Mm.
So you can just tap on the.
So,
Okay, do you have it now? Is it okay if I look at it at the end after answering just
Yeah.
other questions if anyone has it? What time did you come? Mhm. I saw what time you came in at. Nope. Uh, okay. Who wants to go next?
What homework do you said you would consider and you give me
Oh, right. Yeah, I didn't. I have that written. There's a lot of stuff that I have to do towards the end. Um, a- and once I put everything up, before I like finalize it, I'll just if there's anything that I missed or if you have any questions or whatever, you can email me or post on Piazza. But I have your I have it written down, so I didn't look at any of the grading related stuff yet. I didn't get the chance to do any of that.
questions. Fine. Okay, MCQs or short answers.
See, I'm not gonna try to um, cheat you out of a good grade, basically, by giving you something that's very different from everything that we've talked about or the way we've approached things. I I can't share a sample question paper with you because I don't have one. Um, I didn't get to see any of the last few finals. I'll try to get that, but that's not something that I have any guarantee that I'll get. So I was just gonna.
Typing, writing, or
That you won't have to write descriptive answers on paper. If I do ask you to have anything long form descriptive, you'll be typing that. Um, Solving things, I'll try to structure it in a way that you can just like type final answers in. I don't know if it's possible to have a matrix to like plug values into on UV learns, but if that's one way I can do it, then I'll do it that way. If not, I'll just give like position coefficients like A1, 1, 1, 2, 1, 3, whatever, and then you just fill out the values for those as a list of values or something like that. And yeah, I'll give you like scratch paper to solve stuff.
so the last time we asked you questions, similar kind of question.
Yeah, I'm just saying like the format of question, not necessarily content or level of difficulty that you shouldn't extrapolate one to one. Just be familiar with the things that we talked about in class, how we think about all the concepts and whatever is on the slides. If it's like a derivation or whatever, I don't expect you to have that memorized, but just sort of understand what is happening between steps. Yeah, you were saying?
For homework 3 and 4, it's a completely different written assignment compared to 1 and 2.
Yeah.
It's based on the.
Yeah, so there's nothing I could ask you to like calculate that deals with ML or deep learning type of things, right? So it makes more sense for me to ask something that's tests your like subjective understanding of what's going on. And it also has the benefit of everyone having a different understanding that should ideally have some variation across all the answers I read. So that was another goal of switching it up like that. Yeah, you're welcome.
Part, it's like no need to use latex, right?
No, I mean, considering the time, you're fine
Is
not
it
using.
possible to like get rid of the latex requirement for project report because it's very tight constraint or time constraint?
No.
Because like it's too much time.
No, I mean, especially if you see, this is one of the classes where the project is eligible for like a master's project. So if you're writing a report for that in just Word, it's not a good look. So, and the project, like you've been thinking of what your idea was and have some sort of understanding of what will go in your report for at least 2 months now.
Yeah.
So yeah, it's not even that hard to go from like draft it in Word or whatever and just throw it into some chat GPT, whatever, and ask it to convert a PDF to latex, and it'll give.
Use the ChatGPT code.
As long as you're not, as long as all the like content in there are words that you phrased and wrote.
Okay. Like
to convert format, I don't care if you use that.
Yeah, then it should not be a problem.
And for phrasing and stuff, if you're using Grammarly or whatever, like if it's commas or like spellings, that's fine. But if it's rewriting it to sound more academic or whatever, that is not acceptable.
I know Grammarly I use just to like correct the grammar and for the like just to correct the grammar, not.
No, like changes to style or tone, only punctuation and clauses or whatever. Yeah. Yeah, what's up?
What are the chances of having this next Thursday? Well, I have a minor procedure on Friday, so I have to be a little prepared for that.
Would you be okay with taking it from home, or?
Yeah, I can try to come to class, but I don't know, like I have to stop like solid foods. I have to generate that all day.
I can't tell you whether there's going to be a quiz or not, but I'll take your case into consideration and see what I can do with it. There's a couple of people who have other stuff going on this week, so I have to figure that out anyway. I'll check what I can do about your situation also. No, next Thursday is the final, right? Yeah, whether there's going to be a quiz or not, I can't tell you that, but I'll figure out some way that you don't get shortchanged. Do you have any other questions? Okay, yeah. I'll, okay.
I reached out to Professor Siha regarding that research of.
All right, yeah, he told me.
Yeah. So like, right now we're like busy with this coursework and stuff, right? So I just told him like after 17 I'll be free to work for the stuff and all.
Okay.
But he said it's fine after the summer if we could just start the work. But meanwhile, I just want to get on with the I understand of what thing is. If you have some research articles or something, which I could just.
I can explain what the project. Did he tell you what he has in mind?
He said me that he's got a set of images where using
Yeah,
there's some clinical image that we need to be
Okay.
detecting.
I'll talk to you in a second.
Okay.
Yeah, what was your error? Can I see? Oh, you didn't get an error, right?
Camera is getting
Uh,
activated.
Oh, you
I mean,
shouldn't be running these directly.
same way. Or yeah, and then it will get the cancel that with the dots, like
So
whatever.
this right now you're running with can I see?
This is accurate.
Okay, this oh question. Mm. How long does it take for one frame? Do you know?
Yeah.
Oh, okay. So one of the things is your camera is a lot more high res than mine, so just a lot more computation. Maybe resize the image first before you start doing all of it. So
And also I'm using the seven.
that will
More
also
combinations. I won't be
increase.
able to cancel. Try to cancel that just directly.
Yeah, definitely resize the image so it's smaller, and that should speed things up a little bit. And see if the
But the
OpenCV one is working. If that works, then so there's the flow computation step that is performed before the display step, right? So computing it for one step is why it took so long to open up in the first place, and then after that you have to compute it again for the next pair of frames, so it'll stay frozen while it's doing that, however long it took for the first one. Or yeah, so it updated, but yeah, it's incredibly slow. So passing a smaller image will immediately speed things up a little bit, and then beyond that,
So the distribution shows like we have to 4 parts and it's integrated. Like Python 5,
what does the written part ask for?
not the written part. Talking about the
No, I'm in the written part. Have I asked for a comparison or just your thoughts on
this
I to explain the principles, assumptions, analyze the strength and weakness, explain compare the performance, yeah, of each
so this will be
variation. So just put
time.
screenshots. Performance is not just like frame rate and all of that, but like how good your flow vectors are. What do you think about how it looks compared to Raft and OpenCV? Uh, like just generally, if you have vectors going all over the place, then it's not a very useful. You can't do anything with it. So that's
This
also
comparison is
include.
about the application, 3 to 4 application what you provided, or is it about the variants of Lucas where can it
The different versions of Lucas Canary that you implement, um, how
that only
those compare to each other, and just overall generally
the application?
how it looks.
I mean, I have taken a screenshot.
Yeah.
Like
So
screenshots are there. Like I have all the screenshots here. This
yeah,
will be
that's
comparison, right?
mhm,
Something like that.
yeah.
Or you are saying like in the application part we need to show if we integrate this.
No, so what I'm saying is you don't need a video because I'll be able to see those things and
This
sort
notebook
of
is separate.
guess what your implementation was. Yeah, this notebook plus
I have
whatever you
added
put
the
in your
screenshots separately. That
i-
should
in your report, you'll have some sort of interpretation of what like your output. Just looking at it, sure, you're able to say how long it took to run them, but beyond that, the quality of flow vectors that you're getting, whether it is what it should be, that sort of interpretation also is part of how the algorithm performs. Does it solve the problem effectively or not?
Right here, it's the schedule and I already followed everything is over here, and also changed the learning system. Yeah, I mean, on the top there's a link. They having their like a demo things. I already done that part. I don't know why it's asking me to redo it.
Okay, so you have Ninja now. So this will take some debugging, and this is something that ideally, at this point, you should have been at this point at least like a month or two earlier, not like 1 week away from the semester ending.
Yeah, because I just changed the system. I used to use the Windows, and it doesn't work very well. So then I changed to this.
What would you like me to do?
So I mean, right now I just got a question. So like, if I'm not able to fix this, can I just use their like online demo things? Use the links over there, drag the pictures, and generate the 3D models out of it. It's not coming from here, it's from the website.
What is coming from the website?
They just have their models on the website. So basically, like a complete function things.
So it's pre-trained? Like I don't know how
It's
instant
not
mesh
yeah,
works.
yeah,
Is
yes,
it
it's not a pre-trained. It's just like what is supposed to work. So it's just like dragging the pictures into the input and generate the output as a 3D model. I supposed to do that in local drive.
yeah.
Yeah, but like right now it's having an issue.
This is going to take longer than just 5 minutes for me to figure out a solution to this. So I don't know. We'll talk over Zoom. Just tell me what a good time for you is.
Today, Friday, late. Or Thursday.
I can't today. I have meetings with my advisor, which I have to prepare for.
It's okay. I send you an email to list out all the
And in the meantime, I would say, so can you open up the main like page for Instant Mesh? Just 1 second. I'll get. No, hang on.
Not this.
Yeah.
Yeah.
Code. Okay, so this is neural, and it uses PyTorch and transformers and stuff. So, to start a demo, running with command line. Okay, so whatever is in run.py, where is that? There'll be some sort of a main entry point to this. You want to see where this is going? Forest, and then loading up configs and stuff. There should be one like overall function that this calls somewhere. So basically what I'm trying to say is whatever this script is doing, the overview of what goes on in run is that there's a model architecture that's defined somewhere in here. There's the encoder here, and there's a decoder, and both of those have weights associated with them, right? They're using Dino as their encoder and a transformer to decode whatever embedding this generates into a CAD model, and possibly some post-processing after that, which I think would be here in for util. Yeah, so using functions from in here, like utils, and using the model definitions from here, you would load weights. If they have pre-trained weights, if you're able to run it directly, that means they have pre-trained weights somewhere that you're able to download and load directly for use. So your script would basically have to integrate capturing images or loading images that you've already captured, loading up the model, loading its weights, and supplying it to the model, getting whatever its prediction is, and converting that. And all of that is already in here. You just have to find the right parts that are doing those things, and have built like a minimal version of it. So that there's a lot of other like convenience stuff and things that make this code base more flexible that you don't really care about for the scope of the project. So yeah, running it directly on the command line that doesn't really fulfill the requirement of the project, because you're not writing any code. So rather than trying to fight your system, or do you still have Windows on here, or is that? I would just stick with that and try to, I don't know, just whatever you're most comfortable in, try to understand the logic of the code and find which parts are doing what things at just an abstract level rather than at like individual tensors or whatever. You don't care what the individual variables are, just what each function is doing, what it takes as input, what it returns as output, and see which of those you would need, and you need to have an idea of a pipeline that goes from a bunch of images to CAD model. Well, what are the intermediate steps there? And this has a bunch of utilities and functions that already solve all of what you need to build your pipeline. Yeah, you're welcome. Okay. Just give me 1 second.
Just waiting.
Oh, okay. Uh,